And well, everyone, welcome back to the String Theory seminar series. For today's first talk, we're very happy to have Chuying Wang, who will tell us about what type 2B looks to a string. Please take it away.
Okay, thanks a lot for the invitation from the String Final online seminar organizers. It's a great pleasure for me to talk about our recent work here. It is also my first String online Final seminar talk. The title is What 2B looks to a string Cobordisms where non-compact CFTs. This work we finished in this March with my collaborator Eduardo, Anastasi, Miguel Montello, and our supervisor Angel Ulanga. My talk will be divided into three parts. The first part, I will introduce the concept of non-compact Cobordisms. And the second part, I will talk about the 2A and 2B domain wall we constructed. And the third part, I will talk about the fate of branes. More specifically, I will only focus on D-branes and NS5 branes. Swampland Cobordism Conjecture says any proposed quantum theory of gravity with non-trivial Cobordism classes in the space of configurations belongs to the swampland. At a practical level, we use this conjecture as a series of effective field series with ever-increasing better approximation to the quantum gravity. And the underlying Cobordisms groups of this effective field series space of configurations modified order by order, we are including more structures, eventually reaching our trivial trivial quantum gravity Cobordism class. Of course, at the intermediate steps, let's say the theory T-Cobordism, they have some non-vanishing invariants, which obstructs the end of the word boundary description within the theory T. In our work, we provide a new angle to this problem, and we keep the theory T, but allow some Cobordism deformations that may cost infinite energy. In particular, we consider a physical realization of non-compact Cobordism. And I will stress on this point when we encounter where we really implied this concept. Firstly, let's recap a bit of the GSO projection and how historically we consider the connection of 2A and 2B. GSO projection is some operator that can project at the one loop level torus partition function onto states with definite worldsheet fermion number, as well as ensure the modular invariance. If I written down the partition function, one loop torus partition function explicitly, it will be look like this. And with different insertion choice of the GSO projection at the Ramon sector, we can reach either 2B or 2A, and all the massless spectrum I just written down here. And nowadays, we can have a new angle to understand this kind of GSO projection via what is called F invariant. The type 2B superstring worldsheet is endowed with spin times Z2 topological structure. And its invertible physics, or the SPT physics, classified by the second spin Cobordism group of the loop Z2 space, will give us the different choices of the GSO projections. This group is Z2 times Z2, but eventually we will only have two physically distinct type 2 series. As you can see with the rewritten of the torus partition function, we can choose to attach or not on the left sector or right sector the of invariant. With these two different choices, we can reach out to B or to A. We conclude as this picture can be concluded as type 2A and 2B differs by an of invariant. This of invariant also admits the continuum definition, which was carried out by Kitaev. Says upon flipping the mass term sign of a free massive Majorana fermion, one generates a factor of invariant in the partition function. Now I will introduce the supercritical framework, which we used a lot to study the series domain walls in our paper. Supercritical string theory can give superstring worldsheet descriptions beyond critical dimensions. Firstly, we start with type 0 series. There are two reasons. Firstly, in Hellman and Swanson's paper originally, they started from the type 0 series. And also type 0 series is the first step to reach out the type 2 series we want. Type 0 series in flat D equals to 10 plus n dimensions is described by 10 plus D 2D real fermions with bosons and the fermion components forming 1,1 multiplies. And a time-lag linear dilaton must be introduced to balance the worldsheet central charge. The rest are some technical details, because in this kind of story is unavoidably we will have the tachyon, which couples as a worldsheet 1,1 superpotential. The first equation is a tachyon coupling as a superpotential. Upon integrating out the auxiliary fields, we can give the worldsheet potential as shown as the second scalar potential formula here. Requiring the conformal invariance, it will give us the constraints, which is also the tachyon equations of motion, which is the third equation here. The general solution to the tachyon profile looks like the right bottom corner on this page. And depends on the dimensions you start with. You can have different. You start with and arrive in the end. You can have different choices for the type 0 series. For even dimensions, because there is a Z2 symmetry generated by the worldsheet fermion number, choosing opposite or equal GSO projections on the left and right moving Ramond ground states leads to the supercritical 0A or 0B series. But for odd dimension, there is no concept of chirality, so it will only have one option. It was shown in Hellman and Swanson's paper, the whole landscape of dimension quenching transition in type 0 series, as I pasted here at the right-hand side of this page. As you can exactly say, in even dimension, we have two options, but in odd dimensions, we have only one single option. What do I mean by dimension quenching? I give the simplest illustrative example from 11D to 10D. You can also include more dimensions. But this is the simplest one. We take the tachyon profile with the constant coefficient. And at late time, after the closed tachyon condensation, you can say the tachyon profile leads to mass terms to the extra fields. Upon integrating out, this massive 2D fields will lead to the 10D worldsheet contents. This process is called closed tachyon condensation, leads to a dimension quenching. And finally, the theory goes to 0A or 0B, depends on the choice of the coefficients sign. And in our work, we made a slightly different option for this tachyon profile. The prefactor will involve one normal direction. As you can see later, it fits very well to the interpretation of the F invariant and 1D Majorana fermion. The tachyon profile looks like the first equation here. And at late time, it leads to the scalar potential and the Yukawa coupling term as the second equation here. At late time, the tachyon increases exponentially, but the dilaton rose to weak coupling. So we tend to believe this is still a valid effective field theory description. When x9, as you say, from the first term of the second equation, dimension x, the extra dimension is massive and needs to be integrated out. And string propagates only in the rest 10 dimensions. The remaining space-time is given by the locus of vanishing scalar potential. From the second term, x with quadratic term, we can tell it must be the x equal to 0 slice. On this slice, the 11th fermion has the master term as the third term in the scalar potential and Yukawa coupling term. Because this involves the direction x9, so its sign will flip upon crossing s9, which is F stacking we expected. And recall here the definition of the F stacking, which is the sign flip of the Majorana fermion. X9 equals to 0 locus, which is also the domain wall location, is actually non-compact. As you can see, the scalar potential totally vanish. So we tend to believe this is a non-compact direction. So we expect a non-compact Cobordism here. Okay, now we can go to our type 2A and 2B description we want. This is more difficult because type 2A and 2B worldsheet processes Z2 vector times Z2 axial symmetry, which are generated by the which is generated by the worldsheet fermion number and left moving worldsheet fermion number respectively. So gauging the Z2 axial along is anomalous. In modern language, this is captured by the third spin Cobordism group of the loop Z2 space, which is a type 2 case. It is a Z8 anomaly. So it indicates probably we need to involve 8 extra dimensions altogether. Then we will have some problem. How can we gap all these 8 extra directions altogether? Luckily, the recent years flourishing or reflourishing the symmetric mass generation mechanism can be the solution. It can gap the 8 Majorana fermions will preserve Z2 times Z2 symmetry of the type 2 worldsheet theory. But this mechanism, Majorana fermions are represented in spinor representation. So it's more natural to consider the group global form as a spin group. And we also want the F invariant in the end because 2A and 2B differs by the F invariant. So the process is better to be a 2-step process. Firstly, we somehow gauge 7 of them, and with the remaining one to generate the F invariant. And luckily, in Fitkovsky and Kitev's paper in 2009, they have already written down something preserve the spin 7 invariant fermion interaction. And after this intermediate step, one lighter fermion will be preserved. Its mass will generate a stacked off TQFT on the interface after ultimately being integrated out. Okay, now we can try to describe the 2A and 2B domain wall under this framework. If I must use one certain sentence to give the conclusion, our conclusion is we actually don't know. Of course, this, for instance, we don't know if this is transmissible or not. Of course, this is not satisfactory. We can still say something about the property of domain wall from our framework. First thing we can say is it should be located at the strong coupling region. And because this is a quantum gravity theory, so we need to take into account the quantum question after the dimension quenching. In the IR limit of the RG flow, the region near to the worldsheet domain wall, after some redefinition of the fields, we can have a flat metric in strain units and write down a light-like linear dilaton background. Strain propagates freely in 10D in weak coupling region, but the domain wall would locate at the strong coupling region. It is also at finite distance. And for some special cases, especially if the linear dilaton background has some BPS UV completion, as what was carried out in the matrix Big Bang paper. For this case, for the type 2A theory, we tend to believe the domain wall will be a real end of the word boundary. But for 2B, probably at the other side of the domain wall, there can be another type 2B theory. And if this is transmissible or not, we don't know. In fact, whether the domain wall is transmissible or not depends on the non-perturbative UV completion of everything. Now we can try to determine the fate of some branes upon crossing the domain wall. First thing we consider is the D-brane. And the illustrative diagram is here, which is saying the BPS D-brane on one side of the theory upon crossing will change to the non-charged non-BPS brane on the other side. And it's very nice in this picture. Even the trajectory of the 1D Majorana fermion fits very well. It lives on the interface of the two series, as well as the boundary of the worldsheet, which attached to the D-brane upon crossing. With this approximation, it is possible to understand the tension differs of the BPS D-brane and the non-DPS D-brane. Because in our paper, we discussed specifically of the type 0 case of the D-brane, but we tend to believe things would work similarly for type 2 theory as well. And also we discussed the fate of NS5 brane upon crossing. Because there is some anomaly puzzle exists. This question is interesting because there is some anomaly puzzle exists. Type 2B, the NS5 brane is non-chiral, so this side is safe. But for type 2A, the NS5 brane hosts 60 2,0 tensor multiplied, which is chiral and anomalous. I will suggest a solution is NS5 brane incoming from a normal direction, let's say X9, and bends away at the domain wall point to the extra direction X. After integrating out the extra fields, the brane components along the extra dimension becomes defect in the domain wall. And we believe the same analysis will also apply to the T-dot of the NS5 brane, which is set square mod Zn singularities. Okay. In our work, especially today, I discussed the type 2 domain wall and the fate of branes upon crossing the domain wall, which are D-branes and NS5 branes. And probably we can generalize this idea and we can connect a series via the so-called non-compact Cobordism. Type 0 and heterotic domain wall are commented in our paper as well. We hope to come back to especially heterotic domain wall in the near future. And our work was inspired by the work of the Yuping group, which was carried out last year. And another work on the same topic written by Ethan Torres was carried out simultaneously with our work. We want to acknowledge this. Okay, and thank you for your listening.
Thank you for a nice talk. Are there any questions?
Yeah.
Yes, I see MPP. Please go ahead.
Hi, Chuying. It's Ivano.
Yeah. Yeah. You asked
What?
me some question, but I haven't have fun time to reply. Yeah.
No worries, no worries. But I have another one.
Oh, okay, okay.
I was wondering, what happens if you just stay off shell for these, string Cobordisms all the way? Like you stay, let's say in 10D, but off shell. So you don't put the tachyon profile, you don't put the linear dilaton and so on. Or maybe you don't put the linear dilaton, but you put the tachyon profile, for example. Like, can this work out anyway, or like does criticality play a crucial role for you, or conformal invariance?
I think if you want to go to supercritical, you must include linear dilaton to balance the central charge. I've never think of like reconstruct some framework from of this. I think the components are at least essential from the Helwan and Swanson's framework.
Right. If you want to stay on shell, let's say, if you
Yeah.
want the worldsheet background to be good, but
Yeah.
say I don't care about the linear dilaton and I switch it off, and I keep the tachyon profile to do this thing, the dimensional quenching, right? Does this work out a bit differently? Like, does the junction behave differently, or if you have thought about this case?
No, I don't think so. I don't know.
All right. No, okay.
I'm sorry, I don't know.
No problem. Thank you.
Okay, any other questions? If not, then we can thank Chuying again and go on to the next speaker. But yeah, we'll also hang out towards the end if anybody wants to ask more questions in private.
Yeah.